pleasure to be back here. So I was in Stockholm, I don't know how many times, 5, 6, and each time it's very nice to be back. My talk is not necessarily about multi-component superconductors, but let me just show you the next slide, which more or less explains that before we talk about any unconventional orders or unconventional superconductivity, we have to resolve one big controversy which exists in our community. If you're from material science person, doing real materials with real codes, so when you are just down to earth with all the details about the materials, if you ask the question, what is TC if you switch off electron-phonon coupling, the answer is simple, 0. But then there is the other community which is doing unconventional mechanisms, and looks like material science people are saying that if you're doing real materials and we run our codes, there is nothing to look at, because there is no unconventional superconductivity. If you switch off electron-phonon coupling, there is nothing. And that's the problem. So, and the problem more or less is related to the fact that if you do material science code, the most typical setup would be Migdal-Ashberg, solving lowest order diagrams self-consistently for the electron-phonon coupling, and then adding at the end Coulomb interactions as some repulsive pseudopotential. But if you treat Coulomb interactions as repulsive pseudopotential, obviously without any electron-phonon coupling, you have repulsion in the Cooper channel and you are done. There is no TC. So somehow you have to deal with Coulomb interactions in a different way, more consistently. So ultimately you can generate TC at least in some way without electron-phonon coupling. And that's what I know a lot of people are doing and trying to understand, but unfortunately currently looks like the material science community is not there yet. And probably just breaking this controversy is part of what I will try to discuss. I will not solve it for any of the materials, but we will solve it for the Jellium model. At least we have to start somewhere to understand, okay, well, how it works, at least for Jellium. And this will relate to some history. So let me first thank my collaborators on this project. It's Tao Wang, Shanshan Kai, Kun Chen, and Boris Ustinov. Yeah, they are different places now, just moving, defending PhDs. So the outline will be, first I will do a very simple historical introduction just to understand what is the scope of disaster. I'll just explain the gap function equation, how people use the gap function equation to deal with BCS and Migdal-Ashberg type theories. Then what was the Bogolyubov-Tolmachov solution of the Coulomb repulsion problem, which more or less satisfied everybody in the early 1960s. And for 65 years, that's more or less the hoax of mu star, of repulsive mu star. And then I will explain what are the problems with mu star. And there are at least, I know, 5 of them. I'll discuss them one by one, and what is the actual solution. And I'll explain that some of the mistakes which you are doing by implementing mu star are by factor of 2 in the exponent, which means you change your TC by 2 orders up, 2 orders down, 2 orders up, 2 orders down. And maybe at the end, if you neglect all the factors which change your TC by orders up and down and do nothing, you have the right answer. So let's see how this happens, at least for Jellium. So let me start with the gap function equation. You can start deriving it, for example, by looking at the singularity in the pair response function. So I'm talking about conventional orders. So for example, if you add to the Hamiltonian symmetry breaking term, which is creating pairs and deleting pairs, for example, uniformly at 0 frequency, then you simply write down now, just if you add this term to the Hamiltonian, you have an anomalous average, which is, of course, the source, and then propagation to the final point, to Green's functions. Or you have the source, they propagate all possible interactions with this Cooper channel reducible, but, well, irreducible, sorry, then you just, well, say, okay, can propagate again, interact again, Cooper channel irreducible, and just sum up the geometric series to infinity. This is Dyson type equation. Your anomalous average is generated by the source, and there is also a self-consistent term. And if you want a singular response to eta, which is vanishing, going to 0, you'd better have that the matrix here has an eigenvalue equals 1. And that's more or less how the whole setup works. I can take this equation, which is simply a singular response to the symmetry breaking field. I can transform it identically by simply, I know, taking f, multiplying it by gamma, irreducible 4-point vertex, and just rewrite it in this way. But there is no difference. This is source. This is, again, some matrix acting on a vector. And why the response is singular, that's when the
eigenvalue of this matrix reaches 1. And that's more or less the setup. This is the matrix. If the eigenvalue of this matrix equals unity, you have a singular response. So that's the standard setup. So that's what people usually do. They write down this whole, you can call it gap function equation or just a different name, but that's more or less the setup. You have vector, matrix acting on the vector, and look for the largest possible eigenvalue. Whenever you have eigenvalue equals 1, that's your TC. Your response is single. This is standard diagrammatic approach, and because I am looking at singular response going from higher temperatures, all of this is exact. So as long as you know Green's functions and know the irreducible Cooper pair coupling, this is an exact equation for TC, no approximation. And now just, well, if you ask, okay, how BCS will work in this setup without doing variational response or Cooper problem or standard BCS, that's the solution. You just take this equation, plug in the Green's function to this sum, and consider interaction, which is, say, the proper sign, the attraction, which is some attractive constant for low energies and low frequencies. So this is just the cutoff, say, well below Fermi energy, to simplify things. If I plug all of this up, well, if gamma does not depend on the index Pm, and I sum over all Kms, delta is a number. Well, so that's my eigenvalue equation. Alpha times number equals whatever is the sum of T, G, G equals number. So this is my eigenvalue. The product of two ideal Green's functions can be easily calculated because the sum is taken with the lower frequency cutoff, much smaller than Fermi energy. You can linearize the spectrum and finish the answer. So given this type of formulation, which is exact, BCS is trivial. Bayer Green's function, attractive coupling up to certain frequency scale, you're done. Well, if we go to electron-phonon coupling, that's more or less the same setup. Yes, you have more complicated vertex functions, how you create phonons. Phonons propagate. But ultimately, this looks like your gamma function, Cooper channel irreducible gamma. Yes, it's function of momentum transfer and frequency. But again, it's kind of some attraction for frequencies smaller than Debye frequency, and then it goes to 0. So instead of hard cutoff, you have slightly short cutoff at omega Debye, but otherwise it's more or less the same. You just replace gamma with this one, and you have the solution for the standard electron-phonon coupling. Okay. Probably just one thing. Why it's the whole theory with electron-phonon coupling is so easy, because you can say, okay, what about other diagrams contributing to gamma 4? Say, I know, vertex corrections or more complicated diagrams. The answer is Migdal theorem. Migdal theorem was saying that as long as Debye frequency is much smaller than Fermi energy, all other diagrams like
much smaller.
Much smaller. Debye frequency much smaller than Fermi energy, the standard kind of setup. then all vertex corrections are small. High order diagrams are also small. So you are done, because you know your gamma 4, and you can also calculate the Green's function by doing the lowest order self-consistency, and that's what is known as Migdal-Eliashberg theory. Gamma 4 is already simple. That's already our propagator for the phonon field, which is done. And second, well, you need the Green's function. And the Green's function in the Migdal-Eliashberg theory, because the vertex corrections are small, simply requires that you take care of only one self-consistently defined self-energy diagram, which can be easily finished. Because of the because vertex corrections can be neglected, and that's it. So okay, well, the effect on the Green's function is kind of twofold. First, you normalize the spectrum, so you have some effective mass, and you have also a z factor for the singular part of the Green's function. Again, standard Fermi liquid. The only thing we have to kind of remember that when you take the product of two Green's functions, you have from the regular part you have some number which you will saturate to a constant at low temperature, but if you go to low temperature, the singular part, that's the one which is giving you the law. But then you have to care about the renormalized density of states, which is related to the mass renormalization, and z factor squared, because you have two Green's functions. You need the singular part for the first one, singular part for the second one. That's why it's z squared here. And that's how it works, kind of, if I do Migdal-Eliashberg theory. So you say, okay, well, now I have effective lambda, which is the Bayer coupling times density of states, the Bayer density of states. Well, density of states is renormalized by effective mass, and also z squared. And if you just do it for Migdal-Eliashberg theory, you just end up with it, well, the entire setup kind of works this way. because Fermi liquid factor, that's what we call Fermi liquid factor, z squared times the mass renormalization. The Migdal-Liashberg setup, this is just 1 plus Baer coupling in denominator. That's why, for example, when you see phenomenology by Macmillan, you see a formula which is exponent 1 plus lambda divided by lambda. I probably will not discuss here that Migdal-Liashberg theory can easily fail even for lambda much smaller than 1, but it's a separate story. So that's how people usually do it in material science for the electron phonon coupling. Now just, well, why people did not discuss superconductivity as pairing of electrons for almost 40 plus years, since 1911 till 1957, because there is Coulomb repulsion. And Coulomb repulsion prevents you from pairing. So this was the conventional point of view. So somehow you take care about electron phonon attraction, but Coulomb repulsion is this biggest force. And for a while, people didn't even know what to do it, because if you look at the BCS paper, they say, okay, let's neglect Coulomb repulsion. Looks like total BS approach. But you solve it, and you suddenly see that you can match some of the experiments, especially if you normalize everything by TC. So somehow it worked. And a couple of years later, Tolmachov and Bogolyubov more or less found the solution. So let me that's not how they did it, but that's the essence of the approach. Suppose I have some high-frequency repulsive interaction. And I simply decided to compute what will be the effective low-energy interaction in the Cooper channel by simply summing up all ladder diagrams when I have Cooper pairs propagating at high energies. And I just do the geometric summation, eliminate completely Cooper pairs at high energies, and simply see what happens for low-energy scattering. Cooper pair at low energy, Cooper pair at low energy, and in and out. But in the middle, I have Cooper logarithm. But now just, well, if I have repulsive interaction and I just sum up all the letters, that's the answer. It simply tells you that low energy repulsion between the fermions will be the Baer repulsion divided by 1 plus G rho f, dimensionless coupling, times the log. Well, if it was attraction, of course, this ultimately leads to instability because you have 0 in denominator. But if it's repulsion, it simply makes repulsion weaker. And that's how you can more or less now argue about the Coulomb interactions. You start with some strong Coulomb repulsion at high frequencies, but as you go to low frequency scattering in the Cooper channel, it gets weaker, weaker, and weaker, and ultimately, if I take omega c very small, actually it will renormalize to 0. That's how Bogolyubov and Tolmachov more or less explained what happens to the Coulomb repulsion. You have frequency-independent Coulomb repulsion. That's the assumption which they made. You can replace it, for example, by Coulomb interaction divided by Thomas Fermi screening momentum. You say, okay, yeah, kind of slightly inaccurate, but let's buy it. And then you simply say that effective coupling in the material is Coulomb repulsion, which is frequency independent, and then at smaller frequencies, electron phonon couplings comes in. It's not a very big deep. It's not enough to produce completely attractive interaction. No, interaction is always repulsive, but it's weaker at lower frequencies. But that's enough. Because now the argument is that, well, if I renormalize the Coulomb repulsion from higher frequency to lower frequency, it will drop to a smaller value. Then the electron phonon attraction will kick in, and the ultimate sign can be negative. Okay? Well, but what Anderson and Morel did in kind of 3 years later, they simply introduced the notation. So this was Bogolyubov-Dolmachov solution, and Anderson and Morel give it a notation. And that's, since then, this is known as Coulomb Pseudopotential. Now, why it became popular? Because it looks like the formula is pretty universal. First, it's convincing, looks like. And it gives you positive number. And this number is pretty universal in the following sense. If the log is large, JC rho f will cancel. But then if you actually play something naive, use this type of coupling, completely screen Coulomb interaction with Thomas Fermi screening momentum, plug in the numbers, then this is just 0.5. You plug in the logarithm of, say, 200, typical for conventional superconductors, and you get a number which is 0.14. And that's precisely what material science phenomenology is using. That you have to use some number for Coulomb repulsion, which is between 0.12, maybe 0.15. But if you miss the target, you just change it a little bit. Because you're not deriving it. Because all of this is kind of half-assed phenomenology. But that's more or less the argument how this was done. But now just, okay, what is, probably I will skip one piece. If you're interested, then it's later. The gap function, if you solve it for this type of gamma, has a node. The node will happen roughly at this frequency. But what is probably less appreciated is if I solve for the eigenvalue for this type of gamma. The eigenvalue is not a linear function of log t. That's what you have in BCS. In BCS, the eigenvalue is simply linear function of log t. But if I have this type of potential, the eigenvalue is a non-linear function of log t. Actually, it saturates to a certain constant. If constant is bigger than 1, fine, you have superconductivity. But if the constant is 0.9, there is no superconductivity. But if you try to extrapolate from sufficiently high temperature and try to assume that linear extrapolation is allowed, you will be wrong. So just one remark. Now, just what is wrong with the conventional point of view? Well, first, Coulomb interactions are screened, but only at zero frequency. But the way how this was used, it was used at all frequencies. As if I take totally screened Coulomb interaction and apply it, assuming it's repulsive like that, at all frequencies. But this is fake, because Coulomb interactions are not screened at high frequency. They're just bare Coulomb interaction, 4 pi e squared q squared. That's how they are not screened. And only below the plasma frequency, or sufficiently below the plasma frequency, complete screening will happen. Because this is a function of frequency, and that's the actual screened Coulomb interaction. It's a dynamic process. So that's how, for example, for small q, the repulsive Coulomb interaction will look like. That's how it will look for q comparable to K Fermi. And suddenly you realize that this curve is no different from what I was showing you for electron-phonon coupling. Yeah, there was a frequency separation, but then electron-phonon coupling was allowed to be smaller than the basic repulsion. But here you have the same dip. Your repulsion is weaker at lower frequencies. And the moment you see this curve, for the effective coupling in the Cooper channel, immediately think that's probably already superconducting. And that's precisely what was established very quickly. Probably it's on that slide already. By Takada first, then it was repeated by Rachel and Sham, same as Con-Sham. Well, we also repeated this calculation in a slightly different context for many more kind of symmetry channels. The answer is the same. So if I replace static Coulomb repulsion at all frequencies with true dynamically screened Coulomb interactions, say at the RPA level, so this is at the RPA level, and you start computing the mu star, what the Coulomb interaction give you at low frequencies. The other is that mu star will change sign purely at the RPA level, close to RS equal 2. The mu star will become attractive. Well, if you go with some vertex corrections, which are done in a certain way, the answer changes, which is already a sign that probably at large values of RS, vertex corrections should be taken care of more accurately. But if you do it kind of in the easiest possible conventional way, how you screen Coulomb interactions, the answer is for material science systems, which is RS 4 or 5, there is no Coulomb repulsion, there is Coulomb attraction. You switch off Coulomb electron-phonon coupling, and at the RPA level, you will find that it's a S-wave superconductor. So, which means that everything about Bogolyubov, Tolmachov, Anderson, Morel is a total hoax. The moment you do the better job, a little bit better job, you take Coulomb interaction and screen it at the RPA level, you end up with attractive pseudopotential. So that's problem number one. I probably skip on this phase diagram. It's simply just our calculation, which was showing, okay, well, maybe for small RS, this is what's done in 2D. For small RS, everything is accurate at the RPA level, and then you see which phases are superconducting, P, D, F, and at what particular value of RS, which phase is dominating the TC. S wave happens at RS equal 1, and the waves should vary, because probably this is already not perturbative, and the result is not necessarily right. But whatever happens at small values of RS is right. So yes, Coulomb interactions, that's what will happen at the RPA level. The phase diagram of superfluid phases in the 2D electron gas at the RPA level. It's superconducting, including S wave. Now there is, I probably switched the second wrongdoing. The second wrongdoing is simply pure math, just without any reference to any mechanism. It's very simple observation. So if I have one mechanism, remember that I'm talking about largest possible eigenvalue. So I have mechanism A, it has the largest eigenvalue lambda A. You have another mechanism B, it has the largest possible eigenvalue lambda B. But if I combine two mechanisms, it's the same as combining two matrices, because each interaction is a matrix between initial frequency, final frequency, initial momentum, final momentum. If you combine two matrices, the largest eigenvalue for two matrices is always smaller or equal than lambda A plus lambda B. Of course, it's equality if one of the matrices is simply just unity. So frequency and momentum independent, and yes, the eigenvalues will simply combine the easiest way. But in any other case, it will be inequality. So lambda AB will be always smaller than lambda A and lambda B. And that's very simple because the largest eigenvectors for matrix A and matrix B are simply incompatible with each other. They're different matrices. So whatever is the good eigenvector for A is probably very bad eigenvector for B, for different matrices. And actually, you can easily cook up an example when you take one superconducting mechanism, another superconducting mechanism, you combine them together, and the system is not superconducting. So which means two superconducting glues can annihilate each other to nothing. Examples are easy. It's kind of, as a proof of principle, it's easy to do. So which means you have to be careful when combining two mechanisms. Don't use the second mechanism as a number, as if it's a function of frequency and momentum. You're doing a mistake. Big mistake or small mistake is a separate question. But mathematically, this is not rigorous. There is another kind of big wrongdoing by using Coulomb pseudopotential. It's the Fermi liquid factor. If you take gallium, which can be now done very accurately to a sufficiently high order, this was not possible before, but now this is beyond any kind of reasonable doubt. And you compute, say, the Z factor for the electron gas in gallium. Well, for reasonable values of Rs, 4 or 5, that's material science, the Z factor is already 0.65, and then it's getting down. But remember that whatever you put in the exponent has Z squared. 0.65 squared, it's 0.36 or even 0.3. You are making a mistake in the exponent by a factor of 3 by not doing Z factor coming from Coulomb interactions. People do it from electron-phonon coupling, but not from Coulomb interactions. So you probably fake the exponent by a factor of 3 by not considering Z factor coming from Coulomb interactions. You also have an effective mass. So if you are not doing proper calculation of the effective mass, you do, say, the easiest possible GW, self-consistency. GW for the electron gas, it's more or less an equivalent of Migdal-Ashberg for electron-phonon coupling. It's lowest order self-consistent diagram for self-energy. Well, the effective mass is also normalized. Not as much as the Z factor squared, but okay, 10%. Again, everything is in the exponent. There is also kind of more wrongdoing. Probably I'll just give the whole slide. It's easier. There are vertex corrections. Because whatever is Migdal's theorem for electron-phonon coupling, you definitely do it wrong for Coulomb interactions. There is no small parameter to dress the vertex by Coulomb interactions. Or just add ladder in the particle hole channel. And those diagrams are equally important, and probably if you do high energy elimination of high energy space and you look at the effective coupling at low energies in the Cooper channel, you not only have to eliminate Cooper pairs at high energy, you also have to eliminate particle hole channel and other diagrams, I don't know, whatever you can draw at sufficiently high order. All of them are probably important because for RS equal 4 or 5, you don't have small parameters. You have to include vertex corrections in the calculation. If you don't do it, probably you simply gamble with the answer. Okay? And none of this is done. So I would say just the conventional material science code people usually, I'm not saying everybody, but usually, will ignore dynamic screening, which can change the sign of mu star, ignore Z factor coming from Coulomb interactions, ignore the effective mass, ignore the vertex corrections, which will renormalize electron-phonon coupling, including, and ignore high-order diagrams from the Coulomb interaction. Ignore everything. Okay. Now just, what can you do? Well, okay, we are specializing in high-order diagrammatics for the fermionic system when you actually go to order 1, 2, 3, 4, 5, 6, maybe 7. And there is a special technique which was used in this case. It's called variational diagrammatic Monte Carlo, which means you do expansion not in the original interaction, you do expansion in the screened interaction, and then restore the proper screening by using counter terms. Which means the technique itself is completely unbiased. But since you are starting, your starting point is kind of arbitrary, but this arbitrary addition is subtract it term by counter terms, everything is perfect, as long as you go to infinite order. But variational principle simply says, okay, make sure that your arbitrary parameters are tuned to a point when the final answer doesn't depend on the free parameter which you are using. Okay? So you all can always, just let me illustrate. You have a Hamiltonian H to solve. I will solve H1 plus delta H. And delta H is H minus H1. You say, okay, trivial. But maybe H1 for me is more convenient. And then I will do a perturbation theory for H1 and perturbation theory for H1 minus H. So ultimately I will restore everything for H. But you say, okay, but your H1 has an arbitrary, say, amplitude lambda. But say, but final answer, it has to be lambda independent because it has nothing to do with H1. It has everything to do with H. But then you say, I will tune lambda order by order to a point when the answer does not depend when I do the variation in lambda. So you simply look for how your answer order by order depends on lambda by doing the derivative, d over the lambda, and make it a 0. And that's how you select lambda parameter order by order. So that's called variational principle. It was not proved mathematically to kind of mathematically rigorously how it works, but it was tested on many, many systems, and it does miracles. For example, for unharmonic oscillator, you just easily get very accurate answers almost for nothing. Even though expansion in X4 for harmonic oscillator, of course, is known to be divergent. So that's the technique. So that's what was used here to sufficiently high order. And let me now just show you the results of this type of calculation. Some of them were not done by myself or Boris or even our students. Some of this was done by Kun Chen and Christian Howley. I probably should be showing their names. Yeah, I see. So that's what you have for the effective mass. Remember that at GW level, effective mass was dropping by at least 10%. Well, but now if you do high order calculation for the effective mass, in the past people did different type of approximations. For example, not GW, fully self-consistent, but G0W0. You say, okay, why going to lower order self-consistency or even no self-consistency? No reason, just that's what people use, blue curve. Then people will say, okay, there are some vertex corrections, probably you have to take care of them, and there were just a bunch of different curves. The correct answer is given by the dashed maroon line, so those are the data. Now those data are actually known with much higher accuracy, and that's the answer. And you see that for RS equal 4 or 5, typical material science range, the effective mass renormalization is less than 1%. I have no explanation for why, because at the GW level it's already 10%. But the exact solution is less than 1%. Okay, don't worry about mass renormalization. If you did nothing, probably you did it right. Even though I don't know why. That's for Gelium. Of course, for any other material science system, this may be different because it has to be checked. Vertex corrections. This is now the statement which says, okay, well, we know that, for example, for zero frequency and zero momentum transfer, there is kind of word type identity which says effective mass renormalization, or Z factor. It's the derivative of d sigma over d omega, can cancel with vertex corrections. And that's why you have very good motivation actually not to look for the diagrammatic series for Z, which I already showed to you. It was just dropping significantly to 0.65 or even below, but to do the diagrammatic expansion for the product. Quasi-particle residue Z times 3-point vertex dressing the electron phonon coupling times, well, this is simply coming from the fact that, well, you couple to the ion through the Coulomb force. When you couple to the ion through the Coulomb force, there will be screening in between. So electron couples to the charge. Of course, it's bare Coulomb interaction, which you differentiate to get the displacement of the atom. But, well, okay, it's Coulomb interaction, but it is screened Coulomb interaction. Because you cannot couple directly, you can couple through the polarization bubbles in between, as usual. Previous calculations already knew what is W. This was done to sufficiently high order and well converged, so we know this function to 3 digits for any value of Rs. This was done in the past. Well, now just multiply the Z gamma 3 expansion by the W value. So everything here is done up to diagrams 46 for every single value. And you just plot it. Those are the data. And then there is material science practice. Sometimes, well, that's how people look for bare electron phonon coupling and maybe kind of change it a little bit due to screening. And they did it through pure polarization. They say if you do RPA, yeah, you screen everything by the Coulomb interaction is screened by the bare RPA polarization function. But if it's not exact, people have some semi-phenomenological fixes, how slightly modified by adding so-called exchange correlation kernel. But again, there is no Z factor here, there is no gamma 3 here, just pure proper screening of Coulomb interactions between the electrons and the ions. And that's how it compares this formula, which neglects many things, and this formula, which takes care of everything. Z factor, 3-point vertex, and the proper W. More or less, this is the statement that probably the way how this exchange correlation kernel is doing it's pretty good job on the actual screening in metals, but Z gamma 3 is extremely close to unity. Even though Z itself is a meaningful function, it just changes by 40%, but so is gamma 3, goes up by 40%. Altogether, well, okay, you can see the curve. First, the curve is very close to 1, and second, okay, this formula is barely different from the exact calculation. Well, now the final, and the final is more or less something which we didn't appreciate at the beginning ever. It's Tolmachov log, that then if you do dynamic screening, it can even change sign, but if you add high-order diagrams, including cross diagrams, which are particle Hall channel. This is everything up to second order, and those are simply counter terms because expansion is done in screened Coulomb interaction. And then you go all the way up to sixth order. Of course, I cannot draw diagrams even of third order. This will occupy the entire page, then fourth, then fifth, then sixth. There are hundreds and hundreds of diagrams. But if you just do the entire calculation, that's the answer. You compute low energy effective coupling in the Cooper channel and the Fermi surface. That's what you get from, more or less, if it's static screened interaction, this is no different from Tolmachov-Bogolyubov. Well, but then you say you start introducing dynamic screening, but at the same time you add ladders in the particle fault channel, renormalization, because okay, those diagrams are also included. This is the renormalization of the Cooper vertex. It's not gamma 3 because for electron phonon coupling this was gamma 3 at zero frequency. You renormalize by gamma 3 electron phonon coupling. This is simply goes to the effective gamma 4 for the Coulomb interaction. All of this. And you see, okay, well, you go second order, third order, fourth, and sixth. So more or less you saturate that, yes. Ultimately, Coulomb interactions are repulsive in gallium. Again, for any material science system, this may change because it depends on the band structure maybe and many other things. But at least that's the job you have to do. And you see that, well, any smaller type of approximation, replace everything with a static potential is probably wrong. Do dynamic screening at the RPA level is also wrong. Just do everything together and suddenly you recover the answer, which is more or less where we were before, with small changes. So that's my conclusion. So yes, formally material science practice is doing 5 mistakes in a row. Some of them are severe by effect of 2 or 3. Some of them are less innocent. Some of them is a total hoax. For example, Bogolyubov-Tolmachov log or Anderson-Morel argument is total nonsense because dynamic screening immediately changes the sign. But high-order diagrams bring it back to the value which is more or less consistent with what material science practice is, around 2.15. But you have to do all of this together to have the final outcome that material science practice happens to be reasonable. Of course, nobody is questioning it's reasonable because it was tested on an enormous number of superconductors, conventional superconductors. It does work. Simply the problem was that nobody had a clue why. At least for gallium, we can see all the pieces together, how they cancel each other. So if you neglect this, neglect that, neglect this, why this is still reasonable. But if we want to go for unconventional mechanisms in a particular material, we have to implement all of this once again, but now just for a particular band structure and for a particular material. Doing half-assed job when you just do something and don't do something else probably is a big mistake. Okay, I'll stop there.